Hello students, welcome to another video of metric space. In this second video, we will see some examples on metric space. So, first example is, let X be a non-empty set. Let X be a non-empty set. X be a non-empty set. Now, and define function d from x cross x to r plus union singleton 0 such that this function defined as distance of xy is equals to 1 whenever x is not equals to y, and this distance of xy is equals to 0 when x is equals to y. That is we have given that x is a non-empty set and on which the function d is defined from x cross x to r plus union singleton 0 as distance of xy is equals to 1 when x not equals to y and 0 whenever x is equals to y. So, there are only two values of function d of xy. Whenever we apply the function d on this x cross y, we will get only two values, either 1 or 0, and we have to prove that this is a metric on x. Show that this example, let's complete the example first of all. Show that this d is metric on x. D is metric on x, or xd is metric space, and this metric, that is the metric defined as distance of xy is equals to 1 and 0 whenever x is not equals to y and 0 when x is equals to y. This metric is called discrete metric. This metric is called discrete metric. This metric is called discrete metric. So, we have to prove that this d satisfies all three properties of metric space, and after that we will say that this d is a metric on x. So, to solve this example, first of all we will prove the non-negativity. Here clearly we can say that there are only two values of function d, that is whenever we apply d on order pair xy, we get either 1 or 0, and these two values are greater than or equals to 0. So, we can clearly say that distance of xy is greater or equal 0 for all xy belongs to x, that is our function d satisfies non-negativity. So, first property is non-negativity. So, for all x comma y belongs to x, if our x not equals to y, then we get, if x not equals to y, then distance of xy is equals to 1, and if our x is equals to y, then distance of xy is equals to 0. This is greater or equal, strictly greater than 0, again this is greater or equal 0. Thus we can say that distance of xy greater or equal 0 for all xy belongs to x, and distance of x and x, that x is equals to y, means distance between x and x. Distance between x and x is equals to 0 for all x belongs to x. Hence d satisfies non-negativity. D satisfies non-negative property or non-negativity. D satisfies non-negativity. Now, the second property is symmetric axiom. So, in the second property, we have to show that distance of xy is equals to distance of yx. Distance of xy is equals to distance of yx for all xy belongs to x. Now here we have two conditions. First condition is x is equals to x not equals to y, and the second condition is x is equals to y. If x is not equals to y, then distance of xy is defined as 1. So similarly we can take this x not equals to y means y not equals to x, and whenever y not equals to x, the function defined as distance of y and x is equals to 1. Suppose if x not equals to y, then distance of xy is equals to, this is the definition of this discrete matrix. X not equals to y, then distance of xy is equals to 1. Similarly, if y not equals to x, then distance of yx is equals to 1. From these, suppose this is equation number 1 and this is suppose second. From equation 1 and 2, we can say that distance of xy is equal to distance of yx, since both are equals to 1. From equation 1 and 2, from equations 1 and 2, we can say that distance of xy is equals to distance of yx, since d set. So similarly we have to prove that for x is equals to y, both the distance of xy and distance of yx are equal. Now this was our first case when x not equals to y. Now in the second case is if x is equals to y. If x is equals to y, then distance between x and y is equals to 0, as function defined as distance of x and y is equals to 0 whenever x is equals to y. Similarly, if y is equals to x, we will give distance of y and x is equals to 0. Thus this distance of yx and distance of xy are same. Thus distance of xy is equals to distance of yx. This is for all x comma y belongs to x. Hence we can say that D satisfies second property, and second property is symmetric axiom. D satisfies symmetric axiom. D satisfies symmetric axiom. Now is it visible? Now we are going to prove the third property. Third property is triangle inequality. So to prove triangle inequality, let x comma y comma z are the elements of x, and our claim is distance of xz is less equal distance of xy plus distance of yz. So now our claim is distance of xz is less than or equals to distance of xy plus distance of y and z. To prove this claim, we have to take some cases, because here x may be equals to y, may be equals to z. So first of all, in the first case we will take our x is equals to y is equals to z. X is equals to y is equals to z. This is our first case. So if x is equals to y and y is equals to z, means when x is equals to y, then distance of xy is equals to 0. Similarly, distance of yz is equals to 0, distance of xz is equals to 0. By definition of function of, that is by the definition of D, you can write this as x is equals to y. This will give distance between xz, as this x is equals to z. X is equals to y is equal to z means x is equals to z, and x is equals to z, then distance of xz is equals to 0. Distance of xy is again equals to 0, and distance of y and z is again equals to 0. And clearly 0 is less than or equals to 0 plus 0. That is, this distance of xz is less than or equal to distance of xy plus distance of yz. That is, distance of xz is less than or equals to distance of xy plus distance of yz. Now in the second case second, we take suppose if this x is equals to x suppose not equals to y, and y suppose not equals to z, and x is equals to z. That is, now if x not equals to y, then distance of x and y is equals to 1, since our function d is defined as distance of xy is equals to 1 whenever x not equals to y, and when x is equals to some y, then distance of xy is equals to 0. Again here y not equals to z, so distance of y and z, distance of y with z is equals to 1, and distance x and y are equal, x and z are equal, so distance of x and z is equals to 0. Again 0 is less equal 1 plus 1, that is distance of this x and z is less than or equals to distance of xy plus distance of y and z. Hence again in the second case our triangle inequality proved. Now third case, now case 3, if x is equals to y, y not equals to z, and suppose again x not equals to z, so again this will give distance of x and y is equals to 0, distance of y and z is equals to 1, and distance of x and z is equals to 1. Again this 1 is less than or equals to this 0 plus 1, that is distance of xz is less than or equals to distance of xy plus distance of y and z. So here again the triangle inequality hold. Now in the case fourth, so if you think if distance of x and z is equals to 1 and these remaining both are 0, that is if you take, suppose just this is rough calculation, if you take this 1 is less equal 0 plus 0, then our result contradicts, that is this is not true, 1 is always greater than 0. But if we get, if you take distance of x z is equals to 1, distance of xy is equals to 0, and distance of yz is equals to 0, and try to prove or make confusion, then it is wrong, since distance of x and z is equals to 1 is possible when x not equals to z, distance of xy 0 means x is equals to y, and distance of yz is equals to 0 means y is equals to z. Now if this y is equals to z, I can read it as z is equals to y, and when this y is equals to z or z is equals to y, if we put the value of z here, we get, if we put the value of z is equals to y, then we get x not equals to y, and which will contradict this, that is here x is equals to y, but if you put z is equals to y here, then we get x not equals to y, so this is contradiction. Similarly we can, therefore we can say that this case is not possible, that is distance of xz is equals to 1 and distance of xy is equals to 0 and distance of yz is equals to 0. This case is not possible, because if you take this, then x not equals to z and z is equals to y will give us x not equals to y, and which is contradiction to this. So this case is not possible. This is just the rough work that you don't have to write in your notebook. Now the fourth case, in the fourth case we will say that both are equal, that sorry both are not equal. The fourth case is if x not equals to y, which is not equals to z. Now if x not equals to y will gives us distance of x and y is equals to 1. Similarly y not equals to z, so distance of y and z is equals to 1, and distance of x and z is again equals to 1, and clearly 1 is less equal 1 plus 1, since 1 is less than 2, that is distance of xz is less equal distance of xy plus distance of y and z. Therefore from above all cases, we can say that D satisfies triangle inequality. D satisfies triangle inequality. D satisfies triangle inequality. Therefore, D satisfies all the properties of metric space. Thus, D is metric on X. D is metric on X, or XD is metric space. XD is metric space. Hence, the example is completed.